In the previous session, we have looked at equivalence of matrices. We have looked at row equivalence, and in that we have seen row echelon form and reduced row echelon form. Let's dig a little bit deeper into this with an example. So we have a matrix A, which is a 4 by 4 matrix. Now, what are the row operations that we can carry out? So let's look at elementary row operations. Row interchange, we can swap two rows of the matrix. Say, for example, R1 and R2 are exchanged. Scalar multiplication. Multiply a row by a non-zero scalar. That is k times R2, for example. So 2, 5, 4, 7 are multiplied by a scalar k. Row addition or subtraction. Add or subtract a multiple of one row to or from another row. So we have R2 plus KR3. Here the result of this operation is put in R2. So R2 gets replaced by the result of this operation. So now let's start with the matrix A and let's carry out the operations. Replace R2 with R2 minus 2R1. So R2 is 2 minus 2 times R1, that is 2 times 1. So 2 minus 2 is 0. 5 minus 2 times 2, that is 5 minus 4 is 1. 4 minus 2 times 2, that is 4 plus 4, that is 8. 7 minus 6, that is 1. Now take this result and carry out the next operation. We replace R3 with R3 plus R1. So R3 is minus 1 plus R1 is 1. So minus 1 plus 1 is 0. Similarly, minus 3 plus 2 is minus 1. 2 minus 2 is 0. Minus 1 plus 3 is 2. Like that, we visualize this, figure out what operation we have to carry out to, our objective is what? To bring it to row echelon form. So what is the row echelon form? We have to arrive at pivots, and under the pivots we want zeros. So here you notice under 1 we have all zeros. Now the second row pivot could be 1. So under that it should be zeros. So we carry out further operations. You can pause this video and just take it step by step and figure out. So we have arrived at the pivot of the second row as well. Under that we have zeros. We have 1, 3. So 1 is okay. 3 has to be 0 now. So that has become 0. And finally, we make this as 1 by multiplying R4 by the reciprocal of minus 33 by 8. That is minus 8 by 33. So this is row echelon form. Okay, so that was row echelon. Now we continue further to arrive at row reduced echelon form. Okay, I'm bringing it again, row echelon form, and we carry out the row operations. Now our objective is to make these values 0. Let's see, R2 minus R4. So R2 is 0 by minus 0. 1 minus 0 is 1. 8 minus 0 is 8. 1 minus 1 is 0. Yes, all these have become 0. Like that, we keep carrying out the operations till these also become 0. we have reached row reduced echelon form, which is nothing but an identity of order 4. As you keep practicing, what will happen is you will be able to write multiple operations on this arrow and carry it out one by one. Now let's compare what we have done using matrices and what we would have done using algebra. Let A be the coefficient matrix. Since only the coefficient matrix is given, we consider the corresponding system A times x equal to 0. Let the variables be w, x, y, z, so that we have A times x equal to 0. Converting this into linear equations, we have 1w, that is w, plus 2x minus 2y plus 3z. Each column corresponds to a variable. Then we have 2w plus 5x plus 4y plus 7z equal to 0. Then we have minus w minus 3x plus 2y minus z is equal to 0. And finally, 2w plus 4x minus y plus 3z is equal to 0. Now, in matrix form, this system of equations is written in matrix form like this. Now, by eliminating variables successively using standard algebraic methods, we obtain this system of equations. W plus 2x minus 2y plus 3z equal to 0, x plus 8y plus z equal to 0, 8y plus 3z is equal to 0, and z is equal to 0. The row echelon form is this: 1, 2, minus 2, 3, 1, 8, 1, 8, 3, 1. Here, if you notice, if you look at the coefficients, it is the same thing: 1, 2, minus 2, 3, 1, 8, 1, 8, 3, and finally 1. So here W is 0, so 0. Here W and X are 0 in this equation, so 0, 0. And here we have W, X and Y equal to 0, so 0, 0, 0. Now we can solve the system uniquely by back substitution. Z is equal to 0, so substitute it back in the previous equation. So 3, 0 becomes 0, 8y equal to 0, y equal to 0. So z equal to 0 implies y equal to 0, which implies x equal to 0, which implies w is equal to 0. Now here we have to bring it to the row reduced echelon form. So here you notice 1w plus 0x plus 0y plus 0z is equal to 0. That means w equal to 0. Here 0w plus 1x plus 0y plus 0z is equal to 0. That means x equal to 0. Similarly, y equal to 0, z equal to 0. So, reducing a matrix to row echelon form corresponds to eliminating variables step by step and reducing it further to row reduced echelon form gives a solution directly. Sometimes we may end up with one or more rows consisting entirely of zeros at the bottom of the matrix or columns without pivots. Here, every row has a pivot, every column has a pivot. Whereas sometimes we may not have such a perfect identity matrix as the row reduced echelon. It might be something like this. Let me bring this here. Now, if I put it here, in this quadrant, we have a perfect identity. So we can write it in short form as a matrix of identity of order 3 and 0 matrix of order 3 by 1. Or we might have this. So here what do we have? Let me again bring this here. Here we have this we have an identity of order 3, a matrix of order 3 by 3, and a zero matrix of order 2 by 3, and again zero matrix of order 2 by 3. So all these are row reduced echelon forms. In such cases where we have rows consisting entirely of zeros or columns without pivots, the system does not have a unique solution. Now here, where does equivalence of matrices come into picture? Let A is a given matrix, A1, A2, A3, A sub k be the matrices obtained during the reduction of A, where A sub k is equal to the row reduced echelon form of A. Since each step involves an elementary row operation, that means all of these matrices are equivalent to each other. A is equivalent to A1, which is equivalent to A2, which is equivalent to A3, and so on till we reach the A sub k, which is the row reduced echelon form of A, which also means that A is equivalent to any REF which is equivalent to row reduced echelon form. Now, rank of a matrix. When a matrix is reduced to row reduced echelon form, the number of pivots in the resulting matrix is called the rank of the matrix. So here in the row reduced echelon form, we had a 4 by 4 identity matrix. So the rank of the matrix A is 4, whereas here the rank is 3. Although rank is defined via RREF, that is the row reduced echelon form, it is a property of the original matrix. Equivalently, it is the number of non-zero rows in the row reduced echelon form. Each non-zero row contains exactly one pivot. Again, in row reduced echelon form, the pivot columns form an identity matrix I sub R. So the rank of the matrix is R. Basic definition is when a matrix is reduced to RREF, the number of pivots in the resulting matrix is called the rank of the matrix. These are other ways of looking at rank. And finally, all row equivalent matrices have the same rank. So A sub 1, A sub 2, A sub 3, A sub k have the same rank. So that was equivalence of matrices.